So, from Kolmogorov theory we can derive a lot of properties of turbulent flow. Okay. So, I will sketch what can you say, like for example, this k eta we can get from Kolmogorov theory, or Reynolds number relation with small size versus big size, smallest grid. So, let me derive one by one. Okay. So, I will derive some of it, and you can find a lot of it in in the notes I given you. Okay. Now, so this is spectrum I derived it, no. So, by the way, pi u and epsilon u roughly equal. There is slight difference, and that difference comes from 0 to k naught integral, where the viscosity effects are small. So, I should have told you. So, difference will be 0 to k naught nu k squared E u k. So, here k is small. Of course, EU could be large, but k square k is small, no. So, that is where viscous terms are. So, this is the difference between epsilon u minus pi u. Okay. So, we assume it to be small. That is why this Kolmogorov theory is assume that your inertial range is really infinitely long. Okay. So, to get rid of all these problems. But anyway, so this is epsilon u. Now, we can say something about what is energy of the large scale flows. So, what is the energy of the full system? By the way, this is, let me also make this remark. So, my full spectrum, let us draw this properly. My full spectrum will look something like this. I am going to derive the right side. I will derive this region as well, maybe in the next class. So, this region we can get under some more assumption, we can derive it. This region is also the theory, but it depends on forcing. This region has no universal theory, forcing band. Okay. But total energy will be the integral over the full box, full wave numbers, right. So, total energy EU is integral of EUK dk. This is 0 to infinity. But in physics we always make approximations. Okay. So, I say, well, I do not know what is this here, but I will say I am going to start not from here, but I start estimating energy from here to infinity. Okay. So, this will be approximately. Now, this side is some function, no. Say, well, that function energy is too tiny that I do not even worry about that part. So, I will say I basically go up to here k di and I integrate. So, this is k Kolmogorov epsilon 2/3 u k minus 5/3 dk. So, I start from system size. So, this I am saying, well, this is basically where is like 1 by length, 1 by system size. So, Kolmogorov theory is applicable all the way up to system size. So, I am basically ignoring this part. I say this is my system wave number. Now, what happens to this integral will be k minus 2/3 epsilon u 2/3 and k Kolmogorov is 1. So, I will not even carry that. I integrate from 1 by length to infinity. What is this integral at infinity? This limit to infinity is 0, right. So, this is basically epsilon u L to the power 2/3. Correct. And this, what is EU is u squared by 2. So, EU there is a 2/3, no, it's 2/3. So, this gives you u equal to, is estimate, it is not really the full thing, but it is estimate u is epsilon 1/3 L 1/3. In turbulent flows, energy at large scale, u is basically large scale, no. This is what is telling you the energy is dominant by small k contribution. In this integral, which is the most dominant part? Small scales are not dominant because they give you 0. Integral dominates from low end. So, these are called asymptotic methods. So, in integral which part is contributing most, and that is what I take into account. So, here U is the total energy is dominantly coming from large scales or low wave numbers, and UL is epsilon 1/3 L 1/3. Okay. So, this is extremely useful result, and this works for atmosphere, for solar physics. You apply some of these ideas in turbulent regime. So, this energy at large scale or velocity at large scale. So, if somehow you can estimate dissipation epsilon, then you have the UL. Okay. So, L is given to you as well. This sun, this big thing is 100 kilometer size, and or maybe 1000 kilometer size, the eddies, and from that you can get how much dissipation is there. We estimate it, and you get how much should be moving, or other way around. We can measure the velocity field from here by some measurements. So, U is known, L is known, then you can compute epsilon. How do I invert it? By the way, this is straightforward, no? What is dissipation rate? U cube by L. So, given U and large scale velocity and large scale L, I can get epsilon U. Now, this is in turbulent flow. Okay. Now, viscous flows I will not do it, but I will leave the exercise is nu U squared by L squared is the dissipation rate. Okay. This for viscous flows, but not relevant for this discussion. Now, this is velocity at large scales, this one. What about velocity at intermediate scales or any scale L? Can we say something about that? In fact, Kolmogorov theory can immediately say something about it. So, let us estimate that here. So, EUK is what? Is basically energy at inside a shell of radius k. So, that should give you velocity field at length scale 1 by k. So, this is now let me make this another remark without proof. I can give my handout. So, EUK is energy UK squared, which is energy at that velocity. UK is the velocity at that length scale wave number k, divided by dk. No, I should divide by dk, but dk is k itself. Dk is not k2 minus k1, but it is just k. Now, it looks very odd. No, how can you make dk is k or dx is x? But this is reasonable for power law physics, where it is like fractal like structure. So, you say how many people have income from. So, basically you divide income in logs, put log scale. So, when income becomes half, how many people are included? Income becomes another half, then how many people are there? So, jump is not delta x, but jump is of the order of the income itself. So, biggest income is now who are the richest people? $1 billion. 1 billion is too much, I think. 100 million, maybe 1 billion. Okay. So, 100 million. So, 100 million you make it half, or not even half. You go to 10 million. So, how many people are there? 10 million to come to 1 million. So, your jump is not delta x 1 million, jump is factor 10, factor 10, factor 10. Is that understood? So, in this physics of fractal or power laws, you make dk as k itself. Okay. So, UK squared, I do not divide by dk, but or dk is 1, I divide by k itself. So, this energy at scale k, well scale 1 by k or wave number k. Now, this is equal to, from Kolmogorov theory, epsilon u 2/3 k minus 5/3. So, this gives you UK squared is epsilon u 2/3 k minus 2/3. Is my handwriting too tiny or it's okay? So, UK is epsilon 1/3 k minus 1/3. You can check that this has dimension of length by time. Yes or no? Epsilon is dimension of L square by T cube and K has dimension of 1 by length. So, that will be, so this is 1 by 3 and this is 1 and this is L 1/3, right, K minus 1/3 is L. So, this is L by T. Now, we can do some more work. I can compute this K eta. So, how do we compute K eta? So, there are several ways. Yeah. So, we say that whatever energy is coming at large scale, epsilon u I just defined is u cube by L, and same energy is cascading down all the way up to dissipation scale. This is not very good actually. I'll do much better estimate than this, more mathematically sound, but these are approximate. This is what normally we hand wave and say, well, this cascade is going from large scale to small scale. In fact, this same is u k cube by k. No, 1 by length will be k. So, this is same as epsilon u. You can just see that k u k cube is epsilon u. They also should be valid all the way up to dissipation scale. So, that means u at dissipation scale k d or k eta, I am going to call it k nu. Okay. So, k nu. So, I will make it a bit bigger. This is u k nu cube k nu, or I want length scale. So, I will say L nu. L nu is a dissipation scale, length scale, where velocity is losing its meaning. Now, from here I know capital L, I know, well, I know large scale u, but I do not know this u and I do not know L nu, but I can use Kolmogorov theory. So, u cube by u k nu cube is capital L by L nu from here. So, we make another ansatz that kinematic viscosity, now viscosity will come into play. Okay. Now, viscosity I need to bring in, it will depend on viscosity. So, viscosity has dimension of length time velocity, right. So, that is the dimension of centimeter square by second. Okay. So, it is at that scale is ULD times UL nu times L nu. So, I eliminate. So, actually I do not do this, this step is not brought in. I substitute this one into this formula. So, epsilon is from here will be UL nu will be this one, I just plug it in here, okay, nu cube by L nu cube, and there is L nu sitting there. So, this becomes L nu 4. So, that gives you L nu equal to nu cube by epsilon 1/4. So, this is a formula for the length scale where velocity is not meaningful, and this is called Kolmogorov length. Okay. So, this you should memorize this formula, nu cube by epsilon to the 1/4. Now, if I forget about epsilon u, that means is when substitute u I may forget. Okay. So, this now, okay. So, this is how we compute it. So, given viscosity and injection rate, I can get L nu. Now, is one funny thing is that this is funny formula, right, because your dissipation length scale Kolmogorov length depends on injection rate. It is not mean free path length, it tells you that, right. The mean free path length cannot depend on how much energy I am injecting. If I inject more energy, then I can push my L nu to smaller value. So, velocity will be more and more meaningful if I push more energy. your vortex at small scale will be stronger with pushing more energy. Okay. So, in wave number Ek it just goes like this for given injection rate, this is my k nu. If I put in more energy, then it is higher and it just go down furthermore. Okay. So, this is important thing which is kind of different than mean free path length, kinetic theory, all that does not work here. Thermodynamics is not working here. Okay. So, it is can be thrown out, not required. Now, one more formula I will derive is Reynolds number is related with the large length scale and L nu. Okay. So, that is the next formula. So, what is the Reynolds number? Is U L by nu. Fine. Now, nu I am going to use this formula. So, U L by U L nu times L nu. But I know what is ratio of the velocity fields. From Coulomb theory, what is the ratio of the velocity field? So, we derived that, no. So, U at any scale, okay, is epsilon 1/3 k minus 1/3 or epsilon 1/3 L 1/3 U L. You can remember that way as well. So, this ratio, this one and this one should be capital L divided by small l nu cube to the 1/3, sorry, and there is 1 L by L nu already. So, what is this stuff? L by L nu to the power 4 by 3. So, L nu is the smallest scale and capital L is the largest scale. So, the ratio is L by L nu is R to the power 3/4. So, this is the ratio of the length scales in the system. Now, turbulence typically, so the smallest Reynolds number you need is something like few thousand. So, let us make for estimation, I will make Re 10 power 4. For Re equal to 10 power 4, which is there in tip, like coffee, if you just stir this, you can get of that order Reynolds number. So, what is L by L nu? 10 cube, right? 10 power 4 into 3/4, so 10 cube. That means my each direction so that is by, so in simulation, what should be a grid resolution? If you want to simulate a turbulent flow of Reynolds number 10 power 4, should be each direction must be 10 power 10 cube minimum, because I want to resolve the small scale, no. If a simulation does not resolve the small scale or does not take into account the small scale, it is not a good simulation, not a reliable simulation. So, you need 10 cube in each direction. So, what is the total number of mesh points? 1 billion. So, just Reynolds number 10 power 4 requires minimum of 1 billion grid points. In fact, we need slightly smaller than L nu grid. So, even bigger than 1000 cube. So, that is why it is a very difficult problem to simulate. Now, if I want to simulate Re 10 power 8, then what happens? It is just going to become 10 power 6. So, we get 1 million in each direction. So, that makes it 10 power 18, which will fill up the largest supercomputer available on the earth. Okay. So, 10 power 8 also we can't go to, and the sun's convection zone has Reynolds number 10, in fact bigger than 10 power 8. So, we can't do it, but sometimes you do not really need to do for, you have to get an idea of what is happening, you do not need to really simulate all of it. So, it turns out that we can get some idea about things by not simulating this big Reynolds number, but you can do it lower. Okay. So, there are some more predictions, but I think I will not get into all that, and let me make one more remark for completeness, but this is again another field. So, viscosity here is non-zero, right, viscosity is non-zero, but small. We want R e going to infinity limit, but R e is not infinity, viscosity is not 0. So, for all this theory, I think I have next slide. So, we assume that R e tends to 0, it tends to infinity, or viscosity tends to 0, but it is not R e equal to infinity or nu equal to 0. This is called Euler flow. If viscosity is 0, it is called Euler flow, and turbulence is viscosity tending to 0. I need a cascade. Viscosity is not there, then there is no dissipation of energy. With nu equal to 0, what is the dissipation? d nu, 0. If there is no dissipation, there is no flux and nothing. So, in fact, if you recall in my flux lecture, I said flux equal to 0 is also a solution, okay, and flux equal to 0, that means it is an equilibrium theory, that means each mode is giving 0 energy to the other mode. There may be fluctuation, but it is not really giving any net energy to other mode. So, we can take lot of Fourier modes in Euler flow. So, I can have, let us say, n cube Fourier modes, but none of them are losing or giving energy. So, it is like thermodynamics. So, thermodynamics, if you, so this is each particle is, each wave number is like thermodynamic particle. So, all of them will have equal energy, is a socialism where everybody has equal money. So, everybody is equal money, then what is the spectrum? So, constant, no. So, EU modal energy will be constant. So, what about cell spectrum? EU of k is a radius. So, in a shell of radius k, in this radius, how many modes will be there? K squared, radius surface area into dk. So, it is k squared dk if you multiply 4 pi, but I ignore 4 pi, divided by dk. So, spectrum is 4 pi k squared, okay, it is not 5 by 3. So, for Euler flow you expect the spectrum to be k squared, not 5/3, and this is equilibrium theory, and this is Kolmogorov is non-equilibrium. There is a net transfer of energy from large scale to small scale. So, though it is steady, but it is non-equilibrium. Equilibrium definition is not that it is constant energy, it means that there is no, equilibrium implies no exchange of energy from one scale to other scale. Equilibrium in all sense, nobody giving anything to anything, it is on the average 0. So, it is a non-equilibrium phenomena where there is a cascade of energy. Okay. So, we will quickly show that Kolmogorov's predictions are seen in simulations, okay, also in experiments, but I will not do it here, I will just show from numerical simulations. So, we will use our code Tarang, and this is 4000 cube simulation and is done by work by a lot of people in the group, Abhishek and Anando, and there are other people who are not around, but so simulation parameters we do 4000 cube. This was, it is not the largest, but it is one of the largest. Now, largest is 8000 cube in the world. So, we can do 4000 cube with our code, which is very big. That's like, so our parameters are viscosity is not 0 or 10 to 0, but 10 power minus 8, 10 power minus 5. So, it is like 10 power minus 4. Our input rate was 0.1 and our Reynolds number is close to 10 power 5. Our k, the Kolmogorov wave number is 660. So, we can compute from our formula epsilon and nu. So, our L nu is pi by 660 So, it is not 2 pi by pi, okay, and the grid resolution is pi by n. So, this is factor 2 is there, okay, this minus half, and so this is not okay. So, pi by 4096 is the grid resolution. So, L nu by delta is 6. So, this is what I said. So, delta is the lowest length scale, and so how many, so if my blob is there, no, this is smallest length scale, there are 6 mesh points. It is slightly over resolved, but we can do a bit better. I can push my Reynolds number even larger, but I should like to keep 3 points, 3 mesh points. Okay. So, these are some numbers which should know, I mean, like, okay. So, this is what I want to tell you. So, our, if this was becoming 1, this number was becoming 1, then I would be I should not rely that simulation. 3 is okay, but less than 3 or less than 2 is bad. Now, dissipation rate, we computed this ratio is order 1, okay. So, the numbers are there in the paper which is about to come, okay. So, this is a spectrum. So, UK, so in fact decay is 1 for us, in simulation is 2 pi box, so decay is 1. So, we can compute spectrum just by putting UK squared at every mesh, every k. So, I sum over all the modes in a shell of thickness 1. So, 50 to 51, 51 to 52, like that. So, this is the number, and k nu is sitting here 660, no. So, everybody knows how to read the log scale. So, where is 200? Now, this is log scale, I mean some people do not know. So, this is 100, this is 200, this is 300, 400, 500, 600, 700. So, 660 is somewhere there. So, log scale between 100 to 200 is this, here to here is 300. So, it is getting smaller and smaller when you go to larger k, and it is a straight line in the log scale. In real, if I plot linear scale, then I will not get a straight line, is power law. Okay. So, log scale is important. Now, Kolmogorov constant we computed is 1.75, it is not 1.6, it is because it is 4000 cube. Now, you need bigger resolution to get. Now, there are other effects, I mean 1.6 is hard to get exactly. Now, you can look at the flux is very flat here, and it is close to epsilon u is 0.1 right here, and it is in the same band where spectrum is 5/3, it better be, no. So, KDI where my power law is not applicable anymore. So, this is KDI, and this region we will do in the next class, how to model that region. It is possible to model, and this region also we can model. So, flux is constant. I hope you are happy with this, this is like Kolmogorov theory we can see in simulation, in action. Now, we can do also shell to shell, which we did in the class. So, we need to read this. So, n minus m, so there are shells, no. So, this shell, giver shell is m, receiver shell is n. So, in the x axis I plot n minus m. So, if 0 means to itself, so 5 to 5, 6 to 6. So, these are numbers here 4, 5, 6. So, 5 to 5, 6 to 6. So, I do not give to myself, no. So, 0, but this is n minus m is 1, that means 5 to 6 is maximum, you see this maximum. Then it decreases. So, this is 5 to 7, it decreases quite rapidly. 5 to 8 is also tiny, after that it becomes negligible. So, it is not only the next neighbor, but it gives to 2 more neighbors. Now, here the depends on the width of the shell, I do not remember right now, but it is I think 2 to the power 1 quarter is a ratio of 2 shells kn plus 1 by kn. These are all power law bins. My shell radius are not linear, I do not bin like 2, 3, 4, 5, 6 for this computation, is bin like this. The ratio of the shell is a constant number. So, or Kn is alpha to the power n. Okay. Now, so this tells you that Kolmogorov assumption, Kolmogorov makes an assumption that energy transfers are local. That means it goes from scale n to n plus 1. Okay, so it is seen here. Is that clear? So basically, you interact in wave number space to the next shell, or in scale by scale, it implies that one scale to the next scale. In fractal, one scale to next scale. You do not jump the scale. In hydrodynamic theory, you do not. Other theories you could, but in this theory you do not. Now we can also do this in a density plot. Now this plot also you should understand. Now this color bar is here, red is here, and blue is negative. Red is positive and blue is negative. Now this is giver, and this is receiver. Okay, m is giver, and so we should let's take one number 20. So diagonal will be 20 to 20, that is 0, so it is green, but 20 to 21 is red, right? 20 to 21 is red, is maximum in fact. So off band to the right is strongest, that means it is giving highest energy to the next shell, and it fades very quickly. So it is fading to yellow, then it becomes very. So this is a region where it is giving, and left is the region where it is receiving from. So 20 receives from 19, 18 and 17. So I am receiving and giving. Okay. So this is what is done. So this is inertia range is somewhere here. This is inertia range, and this is a dissipation range, and dissipation range is zoomed here. So this is zoomed picture. So start from 27. So 27 is sitting here. Okay, 27 to 40. Now this is huge calculation. This really required a lot of time, and this again in the dissipation range 2, energy transfer is local. It's surprising, but it's also local, and this is there in our same paper. Now, so these are basically verification of Kolmogorov theory. Now, some specifics I quickly want to say this, which we will do it is applicable to isotropic flows. So what does it mean? If I look at small scale where 530 is applicable, if I look at any direction, the flow looks similar, is isotropic. But if I apply rotation, then it is not true. Kolmogorov theory will not work under rotation. It's same hydro, but rotation makes it anisotropic and it does not work. Or if I apply magnetic field, it does not work. It's incompressible. So compressible flows, highly compressible flows, it does not work. It's for 3D, 2D turbulence has different theory. Non-zero viscosity I mentioned, zero viscosity, this won't work. And we assume Kolmogorov theory, well, Kolmogorov did not assume, but in the presentation I made, the flux is not fluctuating. Is, we assume a mean flux. So Kolmogorov theory cannot determine the fluctuations in flux. So I should not really say that assumes. I cannot determine fluctuation delta pi u. So that requires more sophisticated calculations, and that is unsolved problem actually. Delta pi u, there is no universal theory. So we will stop. Thank you.